Hi everyone, I'm Mariel von Stein, and this is Automated Environment Reduction for Debugging Robotic Systems. Here we see a basic failure when testing a robot system's navigation towards a goal. The robot narrowly fails to traverse a ditch and is unable to actuate further. Viable paths exist, but it doesn't seem to be able to find them. The debugging process includes the collection and examination of many topics, traces, diagram analysis, and root cause hypotheses. At this point, our attention is split between many sources of information, and we may be too overloaded to reach a conclusion. We must either spend hours wading through the data, or simply cut our losses and allow the fault to persist. How do we simplify what we're looking at? We have several possible root causes for the failure in the original test. A navigation stack that does not account for discontinuous spaces, an excess of environment-derived noise, a LiDAR system that can't reach far enough ahead, or that the critical part of the environment causing the failure is in a place our system doesn't sense. The original scenario generates too many hypotheses because the complexity of the environment is compounded by the complexity of the system. In the reduced scenario, we can clearly see that the scan data leading up to the failure was all infinite values, giving no indication that a ditch was present. This suggests fixes such as angling the scanner, or incorporating the IMU gyroscope in path planning, or eliminating the test altogether, as it doesn't fit the limitations of this build. We've gone over one application of environment reduction, which is that it's easier to debug a failure with a reduced environment. It's also applicable in instances where you want to reduce resources needed to run tests, find the specific circumstances of corner cases, or to precisely specify what subsystems and behaviors are involved in each test. So, our givens are an environment E where robot R fails with failure F. We know that critical environment elements sit side by side with irrelevant ones. Then, how do we remove the grayed out regions? We have several sources of data we can use to get there. Information from the robot, information from the failure, and elements of the world. Traditional software debugging approaches do not leverage the temporal and spatial relations essential to environment reduction endemic to robotic systems. These cannot be discluded because the criteria for successful behavior for robotic systems are often defined according to spatio-temporal relationships with its environment and its resources. Using givens of E, R, and F, we want to arrive at an environment E' that causes F, where E' is a subset of E. The formalism is addressed in greater detail in the paper. Our environment reduction takes cues from established software debugging techniques. We leverage the temporal and spatial relations to heuristically partition the environment, prioritize sub-environments, and reduce the environment and compare the results against the original failure. First, we systematically reduce E to sub-environments, using partitioning and prioritization heuristics that incorporate prior knowledge from previous runs. For example, we can partition on the proximity of elements in the environment and prioritize according to how close those partitioned centroids are to the trajectory of the robot. The second step reruns the test on the set of sub-environments, using an oracle to check for similar failures. As we go, we partition with increasing granularity, performing a depth-first search for a minimal failure-inducing world. We arrive at a minimal failure-inducing world when all sub-environments of the subsequent partitioning have produced a result dissimilar to the original failure, and our partitioning size is equal to the number of elements in the world. Because non-determinism is expected in robotics testing, we've included a deflaking subroutine to handle flaky tests. Deflaking occurs when a dissimilar failure occurs in order to determine whether a similar failure occurs within X reruns of the test. Deflaking parameterization does expect some knowledge of how frequently the failure of interest occurs. For further detail, refer to algorithms 1 through 3 in the paper. Because we are aiming for a locally one minimal environment rather than the true global minimum environment, we perform a depth-first search of the environment configuration space. Generating and processing each level of the tree is determined by the partitioning and ordering schema, which heuristically determines the relevance of the environment to the system behavior. The partitioning and ordering schema we highlight in this paper leverage the aspects of spatio-temporal relationships endemic to robotics. Our partitioning schema are extensible, so they can incorporate any aspect of the scenario that is of interest. The diagrams here and on previous slides have a partitioning granularity of 2, but that is configurable as well. On the left, for example, we partition by spatial proximity. In other words, we perform clustering on the elements in the environment according to their proximity to one another. Then, the resulting subenvironments are randomly ordered when tested. On the right, environment elements are clustered by proximity to the trajectory of the robot. In other words, the trajectory of the robot is partitioned, and elements are separated into 2 or more partitions according to which trajectory segment they are nearest. During testing, the resulting subenvironments are tested in order of which partition contains the lowest average time step at which the robot sensed these elements. These examples show 4 example schema, although others have been tested in our study. These schema are further elucidated in the paper. This example shows the DDENV technique in action. As the algorithm progresses and partitioning and ordering are performed, it will encounter runs in which the manipulated environment is either a success or a dissimilar failure. Once a similar failure is reached, repartitioning is triggered, and that world becomes the new candidate for the minimal failure-inducing world. The process is repeated until the stopping condition is met. As the plot on the right shows, environment size is monotonic decreasing as the algorithm progresses. Our study seeks to answer the following questions about the approach. Research question 1, how cost-effective is our approach in reducing the size of the environment that led to the failure? And research question 2, how do variations of partitioning and prioritization schema affect cost-effectiveness? The robotics platform to help test our approach implementation was a Husky robot guided by the ROS navigation stack simulated in Gazebo. 3 scenarios were designed to answer our research questions. Each was designed to incorporate different aspects of potential deployment environments and test how effective our initial schema could be. In the ditch scenario, the robot gets stuck in a ditch, causing its wheels to lose contact with the ground, and the robot cannot actuate further. This failure is a result of the robot attempting to navigate a discontinuous space. In the rubble scenario, the robot chassis gets hung up on an element in the environment, again causing its wheels to lose contact with the ground. This failure is caused by the interaction of various dynamic elements, such as piles of wooden boards and a cinder block. In the friction scenario, the robot fails to navigate a narrow opening in the environment to reach its goal. This failure is caused by a series of tiles continuously exerting low and high friction on the robot's contact points with the ground over time. Applying our technique to these 3 separate scenarios, we arrive at a collection of minimal worlds with reduction ranging from 76 to 96% in terms of environment elements. This brings us to our second research question, cost effectiveness. All scenarios had the same timeout per test run and had a similar average time to reach their failure of interest. We found that the largest cost on reduction time was the deflaking process. More consistent failures of interest, such as in the ditch scenario, took significantly less time to reduce, whereas less consistent failures of interest, such as the failure brought about by the dynamic pile of boards and cinder blocks, took more than double the time to reduce to a minimal environment. This is made clearer when comparing the number of tests each environment required in order to arrive at its minimal form. We go into greater detail on cost-effectiveness trade-offs between schema in the paper. Debugging failures in robotic systems presents unique challenges. In this work, we introduced a technique for environment reduction to assist the debugging of robotic systems. Our environment reduction technique incorporates several novel aspects, including spatiotemporal dependencies of environmental models, non-determinism endemic to robotics, and systematic strategies inspired by software debugging techniques. We provide an automated framework that implements this technique, made available via GitHub. This framework is integrated with the Gazebo simulator for the manipulation of its worlds and incorporates 3 partitioning and prioritization schema pairings, as well as a failure characterization based on the robot's pose that serves as an oracle. Additionally, it includes a configurable deflaking process to deal with non-deterministic executions. The results of our study show our technique reduces environment size by as much as 96% within a 2-hour window over 3 scenarios on a popular open-source autonomous robotics platform. We find these results promising and show potential for future work. Thank you for your time and attention. I look forward to questions.